Hey everyone, we're going to be starting a new chapter today, chapter 7, which is all about techniques of integration. And here's the idea, the point. When it comes to derivatives, right, we've got formulas that allow us to handle all kinds of functions, right? We've got a product rule, a chain rule, a quotient rule, and so on, right, that allows us to handle various combinations of functions. But when it comes to integrals, integrals are hard, right? There is no one formula that says if you multiply these two functions, then the integral is such and such. There's no product rule when it comes to functions. You can think of the chain rule as the counterpart of U substitution, right? You can kind of think of substitution as the chain rule in reverse, in a sense. And now what we're going to do is see how much mileage we can get out of the product rule. So let's get started here. Let's let U equal f of x and v equal g of x. And we'll assume that these are both differentiable functions. Then the product rule says that the derivative of u times v is equal to the first function times the derivative of the second function plus the second function times the derivative of the first. Now, what I want to do, I want to solve for that piece right there, the u times dv dx. And so what we get is u times dv dx is equal to the derivative of uv minus v du dx. All right, so all I did, I solved for that piece right there, and I wrote it on the left-hand side, and so here's our right-hand side. And now what I'd like to do is integrate both sides with respect to x. All right, so we'll get integral u dv dx dx equals integral of the derivative of u times v dx minus integral v du dx dx. And when we put this together on the left-hand side, then what we'll have is integral of u dv equals, fundamental theorem of calculus says that when you integrate a derivative, what you get is the integrand inside, so that'll be a uv, and then we'll have minus integral of v times du. That formula right there, this is called integration by parts. All right? So that's the technique or the topic, and this is the technique that we're going to be working with today. Right? It's called integration by parts. And when it comes to integration techniques, substitution is still the most important, the most common, the most prevalent. Integration by parts, I would say, is the second, the runner-up, right? It comes up quite a bit as an important technique for integration. All right, so integration by parts is what we want to look at. So let's just start with an example. What I'd like is to integrate x times e to the x. Now, the way this formula works is we want to think of the integrand that we've been given as the one on the left-hand side. So what I'd like to do is identify one portion of the integrand, call it u, and the other portion, call it dv. So in this case, what I'm going to do is I'm going to let u equal x and dv equals e to the x dx. Now, I would like to compute du. Well, du is just dx. I also need to compute v, and I'll explain why in a second. So from u to du, you compute a derivative. From dv to v, I compute an antiderivative, and so the antiderivative of e to the x is just e to the x. And in this case, we don't need to worry about the plus c, right? I just want to write down the fundamental antiderivative. Okay, so now what I want to do, remember, I'm thinking of this as the left-hand side, and I want to replace it, because we know that it's equal, to the right-hand side. And so notice, in my formula, I started off with a u and a dv. In the right-hand side, I need v, that's why I computed v. I also need du, which is why I computed du. And so now let's fill in the blanks. The left-hand side is equal to u times v, that's an x e to the x, minus the integral of v times du, e to the x dx. So this is the essence, the whole point of integration by parts. Starting off with an integral, and I don't know the formula for the antiderivative of x times e to the x. This is new. Right? Up until today, we weren't able to compute this antiderivative. By doing this process called integration by parts, it replaces it with the right-hand side. And on the right-hand side, you need to compute an antiderivative, but it's an antiderivative now of a function for which I know the formula, right? I know how to anti-differentiate e to the x. So let's finish this off now. I get x e to the x minus e to the x plus c, right? So that's the point of integration by parts. You take the left-hand side, think of that as what you've been given. It replaces it with the right-hand side where you do have to compute an integral, but hopefully this is simpler than the original one. It's one that you know how to compute. And so anytime, and I'll write this down later on, anytime if you have polynomial function times exponential function, integration by parts is the way to go. All right, I guess I'm maybe being a little bit strong there. There are certain times when it's rigged to do substitution, but this is a standard integration by parts situation when you have polynomial times exponential. Next example. Let's look at integral of x times sine x dx. So now what I have is polynomial times trig, another situation where integration by parts is the way to go. So I'm going to let u equal x, dv equal to sine x dx. So remember, in the integration by parts, you want to choose one portion of the integrand and call it u, another portion of the integrand and call it dv. And we'll talk about how to make this choice as we go along. So far in these examples, I'm just sort of telling you, here's the right choices to make. So now du is equal to dx and v is equal to minus cosine of x. All right, so what did I do? I took the derivative of this portion, I took the antiderivative here, and now we throw it into the integration by parts formula, and I'm going to have to erase this formula now. So remember, it goes u times v minus the integral of v du. You want to memorize this, uv minus the integral of v du. Okay, so what do we have here? U times v is going to be a negative x cosine of x, and then we'll have minus the integral of v times du, which will actually give us a plus integral of cosine x dx. And then we can finish this off. This will be negative x cosine x plus sine x plus c. Yeah, let's do it right here. Okay, so next example is going to be integral of natural log of x dx. And believe it or not, right, we learned a bunch of formulas involving exponentials and logs, but we don't know how to anti-differentiate natural log of x at this point. It turns out that integration by parts is the way to go, where you let u equal natural log of x and dv equals dx. Now, let's talk a little bit about choices for u and dv. When you choose u, you're going to compute du. And so it's nice, this is one thing that you want to think about, when you compute a derivative, often it makes things simpler, right? Derivatives simplify functions in most cases. And so what you want to do is think, okay, when I choose u, let's see if we can choose it to give us something that is simpler. Also, so in this case, if I choose du equal to natural log, u equal to natural log, then du is going to be a 1 over x dx. Then, for dv, once we've chosen dv, we have to compute v by anti-differentiating. So, you obviously, when you choose dv, whatever you put equal to dv, it's something that you need to be able to take the antiderivative of. Right? In this case, we'll get v equals x. And so now if we throw it into the formula here, what we'll get is u times v, that's an x natural log of x, minus the integral of v times du. And so that'll, sorry, I made one mistake here. That should be a 1 over x dx. And so now when I multiply du times v, that's going to just leave us with a dx. And so now we get x, natural log of x, minus x plus c as the final answer. So think about this as a rule of thumb. When you're choosing u and dv, you want to choose u, hopefully to be a function whose derivative is actually simpler. But definitely, whatever you choose for dv is something that you can compute the antiderivative of, because you've got to compute v from dv. Next example. This will be integral x squared e to the 3x dx. And I mentioned a minute ago, when you see polynomial times exponential, you want to think integration by parts, so that's definitely the case here. So I'm going to let u equal x squared and dv equal to e to the 3x dx. Now, what's the reason for this choice, right? Why did I let u equal the polynomial part and dv equal the exponential part? And you're always going to do that, right? Always choose the polynomial part equal to u when you have polynomial times exponential. Well, the reason, at least in part, is when you compute du, the derivative of x squared is actually simpler. It brings the degree of the polynomial down. All right, so we get du equal to 2x dx, and then v is a 1/3 e to the 3x. And so now when we put this into the integration by parts formula, what we'll get is our original integral is equal to u times v, that's a 1/3 x squared e to the 3x, minus the integral of v times du. So that will be a 2/3 integral x e to the 3x dx. So notice what we have now. We have an integral. When we applied integration by parts, it took us to this formula that involves an integral. And this integral has polynomial times exponential, just like the original did. But notice what happened. We started off with an x squared, now we have an x. Well, if you had polynomial times exponential, well, you can do integration by parts again, where we let u equal x and dv equal to e to the 3x dx. So my point here, when you do integration by parts, it may give you an integral for which you have to do integration by parts too. Du equals dx, and v equals 1/3 e to the 3x. So let's continue with what we have here. And what we have is 1/3 x squared e to the 3x, that's this part right here, minus 2/3 times, now in the square brackets, I'm going to write down the result of doing integration by parts to this piece right here. So it'll be -2/3 here, and then we'll have u times v, so that's a 1/3 x e to the 3x, minus the integral of v du. So that's minus 1/3 integral e to the 3x dx. And now I can just compute this, so this will be a 1/3 x squared e to the 3x. Minus, so I'm going to distribute now, so this is minus 2/9 x e to the 3x. And then it'll be plus 1/9 integral e to the 3x dx. So one more step. Now I've got an integral that I can actually compute. So this will be a 1/3 x squared e to the 3x minus 2/9 x e to the 3x plus 1/27 e to the 3x plus c. So far I've done examples involving antiderivatives, but you can also do integration by parts with definite integrals. So integration by parts and definite integrals. So what we have then, the formula is going to look exactly the same, except I'm going to put limits of integration here, an a and a b. So the integral from a to b of u dv is equal to u times v evaluated at a and b minus the integral from a to b of v du. So the formula is exactly the same, except I add the limits of integration. And notice when you do integration by parts, you're not changing a variable, so you don't have to change the limits. The limits stay exactly the same on the on the right-hand side as they are on the right-hand side. So let's do a quick example of that one, or of applying this. So integral from pi over 4 to pi over 2. X times cosecant squared x dx. Now remember, when you're doing integration by parts, you got to choose a u and you got to choose a dv. In this case, here's the choices that make sense. I choose u equal to x because what happens when you take the derivative, the degree goes down and you actually get a simpler function, a constant function, right? So du equals dx. And then v equals, okay, so can I compute the antiderivative of cosecant squared? Yes. What I get is negative cotangent of x. So now let's throw this into the integration by parts formula. And what we get is going to be, so let's see, u times v, that's a negative x cotangent x minus the integral of v du. And sorry, we have limits here, so this is going to go from pi over 4 to pi over 2. And so then we'll have plus integral from pi over 4 to pi over 2, and it will be cotangent of x dx. Now, we don't officially have a formula for the antiderivative of cotangent, but we talked about this. In fact, when we were learning, well, I think it was last lecture, we actually did, it was either last lecture or 2 lectures ago, we did the integral of tangent, and the way you do that is you think of it as sine over cosine. Same thing here, and I think I said as an exercise, you should figure out how to do cotangent and write it as cosine of x over sine of x, and then when you do substitution, it'll all work out. So let me just write down what the answer is. Right here, what we're going to get is, this will be a negative x cotangent x going from pi over 4 to pi over 2 plus, and then the answer is its natural log of absolute value of sine x. Right, that's the antiderivative of this piece right here. And you go from pi over 4 to pi over 2. I don't expect you to have this one memorized yet. We will soon get to a point where I'll write down the formula, and you will need to have this one memorized at some point soon. And now let's plug in the limits of integration. This will be a negative pi over 2, cotangent of pi over 2, so that's, that's 0. And then we'll have plus, when I plug in pi over 4, we'll have pi over 4 times cotangent of pi over 4, which is 1. Plus, okay, natural log of sine of pi over 2 is 1, natural log of 1 is 0. So it'll be plus 0 minus natural log of the sine of pi over 4, so natural log of root 2 over 2. So in the end, what we get is pi over 4 minus natural log root 2 over 2. Now, there are are certain situations where when you see this type of integrand, you automatically want to think integration by parts. Certain types of integrands should trigger integration by parts in your head. Now, we've seen 3 of those types: polynomial times exponential, polynomial times trig, and then also those involving natural logs, especially polynomial times natural logs. So we've seen 3 of the standards, and now we're going to see one more example. Let me erase all of this because we're going to need some room here. The last of the standard integration by parts setups is a little more confusing, or a little, let's say, a little trickier, and that's the integral of an exponential times a trig function. So let's do e to the 2x times sine of 5x dx. So when you see exponential times trig, think integration by parts. Here I'm going to let u equal e to the 2x and dv equal to sine 5x dx. So when you do integration by parts, you need to choose a u, you need to choose a dv. It turns out that it doesn't matter which of the 2 you choose. So I always choose the u equal to the exponential part and the dv equal to the polynomial part, to the trig part. But it doesn't matter as long as you're consistent, right? And you'll see what I mean by consistent in a second. So what I've done, I've decided for me, when I do integration by parts, exponential times trig, I will always choose u equal to the exponential part. du equals 2e to the 2x dx, and v equals negative 1/5 cosine 5x. And then we're going to put this in our integration by parts formula, and so what we'll have is u times v, that's a negative 1/5 e to the 2x cosine 5x, minus the integral of v du, so that will be plus a 2/5 integral e to the 2x cosine of 5x dx. So we started off with an integral that was exponential times trig. Integration by parts gave us exponential times trig, which means we can do integration by parts again. All right, we started off exponential times sine, now we've got exponential times cosine. So remember I said this thing about being consistent, so I want to choose u equal to the exponential part and dv equal to the trig part, like that. Compute du, 2e to the 2x, compute v, and we get a 1/5 sine 5x. And so I want to keep track of what I have here. I've got negative 1/5 e to the 2x cosine 5x plus 2/5, and now in square brackets I'm going to write down the result of applying integration by parts to this piece here. And so it'll be a u times v, that's a 1/5 e to the 2x sine 5x, minus the integral of v du will be a minus 2/5 integral e to the 2x sine 5x dx. So take a look at what we have now. We started off exponential times sine. Integration by parts gave us exponential times cosine. Doing again gave us exponential times sine. So what I definitely don't want to do is apply integration by parts again, because then we'll just start this cycle and we'll never get out of it. So instead, let me distribute here and actually kind of collect what we have. So I've got negative 1/5 e to the 2x cosine 5x plus 2/25 e to the 2x sine 5x minus 4/25 integral e to the 2x sine 5x. And let's notice that all of this expression right here is equal to our original integral. So I actually want to write that over here. So I've got e to the 2x sine 5x dx is equal to this mess right here. And so notice now what we have. This integral is equal to this stuff minus 4/25 times the same integral. And so now I want to just do a little bit of algebra. I'm going to have to erase what I have here, so I'll erase the stuff above. What I can now do is move this piece right here over to the left-hand side and join it up. And so what we get then, I have this integral plus 4/25 of this integral, so that will give me what, 29/25 integral, e to the 2x sine 5x dx equals -1/5 e to the 2x cosine 5x plus 2/25 e to the 2x sine 5x, and I guess now I need my plus c over here. Okay, now remember we were trying to compute this integral right here, and now what I know is that 29/25 times this integral equals this stuff. So if I want to solve, multiply both sides by 25/29, we get integral e to the 2x sine 5x dx. So multiply by 25/29 here, and this will give us equals -5/29 e to the 2x cosine 5x plus 2/29 e to the 2x sine 5x plus c. That's the answer. And so notice what we did. We applied integration by parts to compute this integral, but I never actually integrated. So I call this technique integrating without integrating. And this is the way it works every time when you do exponential times sine or cosine. You'll do integration by parts twice and then solve doing the algebra that you see right here. This one's a little more complicated. You'll have some in your homework that are like this. Work them out, right? It takes a time or two going through to actually understand what's happening. So let me write down the 4 standard integration by parts problems. Let's say standard integration by parts. So the first one, if you have, I guess I did polynomial. So polynomial times exponential. Right? What's the right choice? Always let u equal x to the n and dv equal the exponential part, so that'll be e to the ax dx. Next example, polynomial times trig function. Let u equal the polynomial part, dv equal the trig part. The third of the standard ones is polynomial, so x to the n times natural log of x. This is the one where you do it differently, right? Let u equal natural log and let dv equal the polynomial part. So you reverse it when it involves the natural log. And then the last one is the exponential, so e to the ax times trig here, where it's either sine or cosine. So remember, you need to be consistent. It doesn't matter, so I'm just going to say let u equal the exponential part, dv equals either the sine or the cosine portion. And then this is the part where you integrate without integrating. Now, there are other situations where integration by parts shows up, right? And so I can't list every single combination of functions for which integration by parts is appropriate, but these are the 4 standard ones. When you see these ones, you think integration by parts immediately. Now, I want to do a couple of examples that aren't maybe quite as straightforward. So this first example, let's look at integral from 1 to 4 of e to the square root of x dx. This one's not one of the standard ones. And our only other technique is substitution. And so sometimes you just need to try something. Integrals, in general, integrals can be difficult, right? And so sometimes you just need to try something. And so in this case, what I'm going to do is I'm going to let u equal square root of x. All right, so I'm doing substitution here. And in fact, I don't want to use u. Let me use some other symbol. How about t? So I'm going to do substitution, but let's call it t instead of u. Then dt, all right, take the derivative. I'm not doing integration by parts. I'm doing substitution here. dt is going to be 1 over 2 root x dx. And if we solve for dx, what we get is dx equals 2 root x dt, which is equal to 2t dt, because root x is equal to t. Now when we substitute, what we'll get is integral. The limits of integration will be 1 to 2. All right, we did substitution, so you need to change the limits. Right, when x equals 1, t equals 1. When x equals 4, t equals 2. And then we'll have a, what do we have? 2t e to the t dt. I kind of wish I would have put my t2 on the outside here. Let me just do that. So the 2 goes here, t e to the t dt. And now, notice what happens. We did substitution, and what did that do? It gave us an integral that is polynomial times exponential. So now you can do integration by parts. I'm not going to do this because we already did this one. Integration by parts, where you let u equal t and dv equal e to the t dt. So this is going to become more and more common as we learn more integration techniques. You will be given some integral, and it will require multiple techniques to actually compute. In this case, what did we have to do? We did a substitution that allowed us or led us to do integration by parts. And then let's look at one more example. This one's going to be integral from 1 to root 3 arctan of 1 over x dx. Sometimes you just have to try something. In this case, what I'm going to try is integration by parts. So I'm going to let u equal something and dv equal something. Now, would it make sense to choose dv equal to arctan 1 over x? The answer is no, because if you chose dv equal to arctan, you'd have to compute v, which would require you to compute an antiderivative. But that's what we're trying to do here. We don't know the antiderivative of arctan. So the only logical choice here is u equal arctan 1 over x and dv equal to dx. Now when you compute the derivative, so du will be, well, okay, so I need to use the chain rule here. So this is going to be a 1 over 1 plus 1 over x squared times negative 1 over x squared dx. And let's clean this up a little bit. This is going to be a negative 1 over x squared plus 1 dx. And then v is going to equal x. So now let's apply our integration by parts technique or our formula. And so what we'll get is u times v. So that's going to be x arctan 1 over x, right? So I'm multiplying here. We're doing a definite integral, so I need to evaluate at 1 and root 3, minus the integral of v times du. So I'm going to multiply these two pieces here, and that will give me, actually it's going to be plus integral from 1 to root 3. And it will be x over x squared plus 1 dx. So by applying integration by parts, we have an integral, and we can compute this one, right? We can do this by substitution. So what do we get? Let's plug in the limits here. Root 3 arctan 1 over root 3 minus, when I plug in a 1, it'll just be arctan 1. And then we still have this integral to compute, 1 to root 3 x over x squared plus 1 dx. Let's see, arctangent of 1 over root 3. What is that? Pi over 6? Oh, okay. I spaced out. Oh, it's pi over 3, right? Because that will give me a sine root 3 over 2 over 1/2, which is root 3. No, it's pi over 6, right? Yeah, sorry. Yeah, so that's pi over 6. So this will be a root 3 times pi over 6. And then, sorry, so arctangent of 1 over root 3, that's pi over 6. And then arctangent of 1 is a pi over 4. And then we still have this integral to compute. And I'm going to do this by substitution, where I let u equal x squared plus 1. In which case du is equal to 2x dx. And so what we'll get is going to be, so this will be a root 3 pi over 6 minus pi over 4 plus 1/2 integral from 2. So when I plug in a 1, I get a 2. When I plug in a root 3, I get a 4. And this will be a 1 over u du. So that's a root 3 pi all over 6 minus pi over 4 plus 1/2 natural log of u. And we go from, and it's officially its absolute value of u, and we go from 2 to 4. And so this will be, final answer, root 3 pi over 6 minus pi over 4 minus 1/2 natural log of 4 minus natural log of 2. You can simplify this a bit. I guess we probably should. So natural log of 4 minus natural log of 2, using rules of logs, that's natural log of 4 divided by 2. And so here, now let's get this in final form. Root 3 pi over 6 minus pi over 4 minus 1/2 natural log of 2. So this one's a little bit more involved. What happened? We did integration by parts. That gave us this function, which I just need to plug in the limits, and then another function for which we, or an integrand, for which we can compute the integral using a substitution. So integration by parts gave us a substitution problem. So remember, integration by parts, this is one of the most important techniques out there. So study, practice these problems. It's going to show up for the rest of the class. And it'll also show up when you're working in Math 143 and 241 also. Okay, all right, so we'll see you next time.